This is the third lecture for Chapter 11, and we're going to start off with vapor pressure. And we can see on this graph that we're looking at, as we add energy to a system, that the number of molecules, it seems that it's kind of going down, but actually if you look at this line here, more of the particles are actually having enough energy to escape. So this is a minimum kinetic energy to escape from the liquid into the gaseous phase. So a larger proportion of the molecules will have enough energy to move into the gaseous state at a higher temperature. So this is the vapor pressure we're looking at here, the amount of gaseous particles that are able to, or particles that are able to move into a gaseous state. And I guess we'll just mention here, so starting off with a substance which is in a vacuum and we're introducing particles into it or a liquid into it, as we begin to heat the substance or get it to a very specific temperature, we can see starting off some of the particles will move into the gaseous state, and this continues. Think of like a 2 liter of pop. If you open it up, you let out all the pressure and the container isn't as firm as it once was, and then you put the cap back on. Some of the gaseous particles are going into the gas phase, but eventually you hit like a break-even point. And this is the first time we've mentioned it. That's called an equilibrium, where you have the same number of particles moving into the gaseous state as you do have particles moving back into the liquid state. So it's kind of like I said, a break-even or an equilibrium. And this is kind of saying the same thing. I guess one thing we'll add is it's happening at the same rate once you hit that equilibrium point. So this graph here, and I'm never a really big fan of this because it puts so many different substances on there. Let's only focus on the blue line, which is for water. So we see as the temperature rises, the vapor pressure goes up. And the magic point we'll really focus on here is right up there. So at 760 torr, or millimeters of mercury, we see that the temperature for water to boil is 100 degrees Celsius. So that comes from, again, down here. So it's a magic point, that is the boiling point of water. We're all very comfortable with it. But notice what happens if we lower the pressure down. Let's pretend that we're in the mountains up in Denver. Taking that line and stretching it all the way across, we notice that the temperature is going to be something lower based upon the vapor pressure. So there's less atmospheric pressure pushing down on the water up in the mountains. There's less atmosphere up in the mountains, and that's going to lower the temperature down to, say, we'll just make it up, say it's 98 degrees Celsius. And then something like a pressure cooker, if we increase the pressure onto something, we can actually cook at a higher temperature. So that's the magic of a pressure cooker, is that we can actually cook at a higher temperature. So the food cooks more quickly. So to give you a different example is that with your mac and cheese on the stove, just because you crank the temperature up and you got flames kicking up the side of the container, doesn't mean your food's going to cook more quickly. It can't, because you're at the same pressure and you're just putting the liquid into the gaseous state more quickly. The food's not cooking any faster because the water is still at 100 degrees Celsius. Alright, phase diagrams, you probably remember these from last year, looking at the solid, liquid, and gaseous states. And what it does is it makes the comparison between pressure and temperature. And again, if we just want to focus on the boiling point of water, we can look at this line over here and see going from the liquid to the gaseous state. This critical point here, just to mention, is a point in which I am at such a temperature that it doesn't matter how much pressure that I push down on that substance, or actually I should say, increase the pressure as much as I want. I can't force these particles to stick in a liquid state any longer. They have so much energy based on the temperature that we see it expressed as, that we can't force them to condense into a liquid state. So it's called a critical point. Triple point, just to mention, is which you have a very specific temperature and pressure, in which you can get the substance to exist in all three phases. And it only happens at one particular temperature and pressure. All right, so this little comparison here is looking at the vapor pressure in an inverse, well, it's kind of a manipulated equation. It's called the Clapperton Equation, and what we've done is we've taken the vapor pressure and we've changed it around to express it in natural log versus temperature. And there's a couple different ways we can express this equation. This is one of them right here. Another one is in which you're looking at two different pressures and two different temperatures. And this is expressed in, of course, a y equals mx plus b style, where b is simply just this constant, which is our y-intercept, and our x is 1 over t. And what this allows us to do is more accurately make an extrapolation or a prediction of what a temperature would be versus a specific pressure, because it's a linear equation. We're actually not really going to use this much. We used to look at it a little bit more, but I believe College Board has gotten away from this. They have gotten away from this. Okay, just a couple more slides here we'll mention here. This diagram here is for a lot of substances that we mentioned. Water is a little bit different, and we'll see if I can get over to that slide here in just a second. Keep moving. There we go. This is the diagram for water, which is somewhat different than the others based on this line here, and I'll exaggerate the line quite a bit there. So obviously you have your blue line there. I'm going to exaggerate it off with that stretched line to make a point. If we were at some temperature, remember this is a freezing point going from the solid to the liquid state. So we got the liquid over here, solid over there. I'm at that freezing point. Well, what happens if I increase the pressure upon that substance? If I increase the pressure at some constant temperature, I'm going to move from a solid state into the liquid state, which is really weird. So as I push the particles closer together, it goes from a solid to a liquid, which isn't what you would predict. So water is different in that perspective. The solid is less dense than the liquid, which of course is why ice floats. Most substances, you saw the curve where the blue line actually shifts. And let me back up and I'll show it on one of those. There we go. So as I increase pressure, I move from a liquid to a solid, which is what you would expect. Water is different from that perspective, that the solid is less dense than liquid. Okay. So I won't spend a whole lot of time on this because, again, I think you did a lot of it last year, and it's really just making the comparison between the different phase changes. The only one I guess we could mention here is carbon dioxide. I don't think I have a slide for that, but let's just call this right here 1 atm. And as I increase the temperature, notice that there is no liquid state. It goes right from the solid into the gaseous state, which is why carbon dioxide will sublimate. And we're getting pretty close to the end. I don't think there was much more we really needed to mention here. And that's it. So that's the end of the lectures for Chapter 11.